तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Okay, we begin our discussion on epitaxial techniques for gallium arsenide, which will be used for high speed devices. Yesterday we discussed in detail how to realize semi insulating gallium arsenide material, okay, because when you want to make a device or integrated circuit, what we have discussed yesterday was you need a insulating substrate, if not insulating, at least semi insulating. For example, if you take SiO2, the resistivity is something like 10 to the power of 14 ohm centimeters, whereas what you can achieve with gallium arsenide as a semi insulating substrate is something like 10 to the power of 9 to 10 to the power of 10. 10 to the 9 is quite good resistivity that you can get. It is not a perfect insulator, that is why it is called semi insulating material. So, we also seen that you can do it in two ways. One, take polycrystalline gallium arsenide, melt it and grow by isochrosity technique. In that point of time, when you do that, what you will get will be unintentional doped gallium arsenide doped with silicon. Okay. Now, then you compensate it by adding chromium, which introduces a deep level at the mid gap. Another approach which is now popular with availability of high pressure crystal growth systems is you make the compound in situ by taking gallium and arsenic. In fact, today you can get 7 nines, not 6 nines, 7 9 purity, 99.5 nines. So, 7 9 purity gallium arsenide, gallium, 7 9 purity arsenic, all those you can get. So, you can get better purity gallium arsenide substrate. So, you grow that, but when you grow, you end up with p-type material if nothing else happens, due to the contamination from carbon, due to contamination from that liquid encapsulant that you are using. These are things that we saw yesterday. Okay. But the compensation for that acceptor level, shallow acceptor, is done by automatically by excess arsenic that is present, or the arsenic which is sitting on the gallium sides. In fact, if you have some vacancies present, when you grow the crystal, you adjust the composition such that you have deliberately gallium vacancies, then some of these excess arsenic atoms will go and occupy the gallium site. That is called anti-site defect. So, you got, so whenever you have got additional level, this anti-site defect is called EL2 level. I really do not have information why they called EL2, it so happened they call it as EL2 level. Instead of saying chromium level, you say EL2 level. It is actually due to the anti-site defect. Okay. Instead of adding impurity, you have the arsenic sitting there. There is no extra impurity that is added. This itself is acting as impurity. So, whenever you have loss of periodicity or loss of structure, you get additional levels, and this gives donor levels at the mid gap. And we have gone in detail. If you have acceptor level shallow, you can compensate very easily without worrying too much whether I am having too much of donor level. Put the donor level at the mid gap. These are some things that we have discussed. So, you do not have to worry about that EL2 name. It is a name given to another, it is name given to the defect which is arising out of arsenic sitting on the gallium side, that is all. So, now having done that, now you see the growth, that is the substrate, and having done that, that red color or brown color is slowly growing here. Okay. That is, I put it back once again, so that you can see it, gallium arsenide substrate, then on the top of that you have that layer slowly growing. That is the layer which is active layer. In fact, I mentioned yesterday, if this is semi-insulating gallium arsenide is chromium doped, you put, before you put this active layer, you introduce a buffer layer, so that the abuse is taken by the buffer layer. In the sense, when you do high temperature processing, all the chromium that is present may go into the buffer layer, and the actual layer on the top does not get affected. But today, with the ability to grow high purity gallium arsenide with the compensation of the EL2, you do not have to worry. You can straight away grow the epitaxial layer on that, active layer on that. Now, what we want to discuss today is about this particular layer. What is that? In fact, you will call this by different names. In the sense, if you have leisure, you will say epitaxial layer. If you are in a hurry, you will say epitaxy. So, when you say epitaxy, it is actually growth of epitaxial layer. So, what is done here is, let us talk of various things. Supposing you are growing silicon on silicon, then that is silicon epitaxial layer. Supposing you are growing gallium arsenide on gallium arsenide, substrate can have any doping. It can be semi-insulating, p-type, n-type. But here what we are talking of, is semi-insulating gallium arsenide substrate. So, you can grow epitaxial layer of gallium arsenide on the top of that. And the layer that you are growing, if you are going by this whatever technique we are talking of, you can adjust the thickness. We can say I want 0.1 micron or 0.2 micron, you can adjust. You can adjust the doping of that level. When you grow the crystal, when you grow this layer, that is the epitaxial layer, that when you say grow the epitaxial layer, the meaning is you are arranging atoms. You are arranging the atoms of gallium arsenide on the semi-insulating gallium arsenide substrate. And arrangement, if you give proper opportunity to these atoms which are being laid out on the surface, it will take the same crystal structure as the substrate. So, that is why that is called, in fact you can call it as autoepitaxy or homoepitaxy. If the substrate is doped differently, but still it is called homoepitaxy. N-type, P-type does not matter. But if the substrate is totally different, for example, when you grow silicon epitaxial layer on sapphire, that is heteroepitaxy. Okay. It is a totally different substrate, but still you can grow a 100 oriented silicon on sapphire, because there is a good lattice match between silicon with 100 orientation to that particular layer, one particular orientation of sapphire. Okay. So, that is heteroepitaxy. Now, the process involved in the growth of this epitaxy, what is that? The process is, two things should happen. One, you must be able to transport these constituents which form this layer onto the surface. If it is silicon, the constituent is silicon alone. You must transport silicon onto the surface of this silicon substrate. If it is gallium arsenide, you must be able to transport gallium and arsenic, both should be transported onto substrate. Okay. How to transport depends upon a particular process that you are using, and you call the particular process by a name depending upon how you transport this impurity, these constituent elements, atoms. Okay. So, that we will see what are the different processes which are involved. Now, you transport these constituent elements, it is not enough if you transport them, you must give opportunity for these constituent elements. Let us talk of silicon, because only one you have to talk of, one element. Silicon atom you have transported onto surface. What does it do? If you transport and just don't, if you have just keep this and transport the silicon atom, it will go and rest there. Okay? That is not epitaxy. It is just dumping silicon there. You do not want to dump silicon, you want to have silicon arranged with the arrangement same as that of the substrate. How can you do that? You must give opportunity for those atoms to move around. It should be able to move around and attach onto some of the sites which you call it as nucleation sites. Nucleation site is actually a favored site which will go and sit. For example, if I have a surface, a slight kink in some portion, there may be number of kinks due to the atom itself or substrate atom itself. On the atomic scale, there is a small kink. It need not be a kink like that, small kink there. This atom that you have put will go and just move around. When it sees the kink, it will just stop there. That's okay. To stop there. That's, we can call it as nucleation site. It also involves proper wetting, etc. So, simple minded thinking will tell you that wherever kink sites are there, the atom which is moving around because of energy given to that. What is the source of energy? Thermal. That is why in epitaxy you must heat the substrate sufficiently so that the atoms have enough energy to move around. So, it will go and attach into the kink sites, and from that kink site it will move laterally, because if I have one atom sitting there here, next atom will come near that, side by side. So, one layer of atoms should be arranged. Once that one layer is complete, next layer grows, next layer grows. It keeps on growing till you stop the reaction. Okay? That is the epitaxy. That is the arrangement of atoms that is being done. That is why this diagram, what we saw, this diagram, you can see, you can watching this, you see, that's the way it grows. I unfortunately you don't see the color there, so it's actually from there onwards, you can see at least the size coming up. If you put like that, you can see that growth. Okay, so that additional layer that is growing there is gradually growing like that. That is layer by layer. Now, this, if you don't provide additional temperature, additional energy for the atoms to move around, what will happen? Room temperature, you cannot have that growth taking place. You will have lumps of silicon or lumps of gallium arsenide coming up, which is no use for you for making devices. But if the temperature is slightly lower than what is required, the atoms will not have enough energy to arrange themselves. You will end up with not single crystal, polycrystalline material. Okay, polycrystalline material, even if the substrate is single crystal. Suppose the substrate is not single crystal. If you have amorphous crystal material like oxide, on the top of it if you grow a layer, that will turn out to be polycrystalline. It can be amorphous or polycrystalline depending again upon the temperature. Amorphous is random, polycrystalline is number of single crystal layer regions which are joined together. Each region has got, if you want to see that one region may be 100 orientation. You will have another region here which is 111 orientation. You will have another region here 110 orientation. I am just arbitrarily putting, it can be 211, 220, whatever. So, you will have all these things coming up, that is polycrystalline. We are not looking for polycrystalline material here, but in silicon technology you hear about polycrystalline material very often. Where do you hear that? It is part and parcel of the present day integrated circuit technology, because it forms the gate region of the MOS device, and that gate region is done not by epitaxy. The temperatures are low. For silicon epitaxy you need about 1000 degrees centigrade at least. If you take single crystal silicon and raise the temperature to about 1000 degrees centigrade and pass silane gas through that. Silane is nothing but SiH4, that is silane gas. If you pass that, at that temperature it is pyrophoric, it will crack into silicon and hydrogen, and that silicon atom will be sitting on the surface. If it is single crystal at 1000 degrees centigrade, substrate is single crystal, 1000 degrees centigrade, you will get single crystal silicon. Okay, and onto that you add arsine. Okay, silane is there. This will give you silicon plus 2H2. So, that is the one which is being deposited. You want to dope to the gas phase, you add if you add arsine, you will get arsenic plus, okay, you will get AS2 plus 3H2 or 2As, that is chemistry. So, you have arsenic doped silicon. You can add phosphine, you get fifth group, phosphorus. So, you can have silicon doped with arsenic or phosphorus depending upon the dopants added. So, what I am trying to bring out is, I took the example of silicon because it is simple to understand. You can grow an epitaxial layer, undoped epitaxial layer, undoped means not intentionally doped, you may have contaminants coming in. You can intentionally make it N type or P type by adding the suitable constituents to the way you bring in the atoms. Okay. So, now here this in silicon, that poly you obtain there due to two factors. One is temperature is about 625 degrees centigrade in the MOS technology. Two, you grow it on oxide. You deposit on oxide, both put together you get polycrystalline 625. You lower the temperature down to 550 degrees centigrade, you will get amorphous. You get amorphous silicon there. Okay. So, it all depends how much energy it has got to move around. At least to some degree of orientation you get if the temperature is 625. Okay. Now, let us not spend our time too much on the silicon epitaxy. Okay. This is relevant silicon epitaxy if you are using of if you are thinking of silicon on sapphire, that is the same process. Silane broken up into silicon and hydrogen. Take a sapphire substrate, jack the temperature to 1000, do the deposition. In fact, that is one of the materials which is used for making high speed MOS devices. So, that is why it is relevant to this particular presentation discussion. But if you are talking of compound semiconductors only, then let us see what are the things. So, that is the basic process that is involved in the epitaxy. Okay. Now, let us talk of epitaxy of gallium arsenide. As I mentioned, one of the requirements is to keep the substrate hot. Other requirement is transport these constituent elements to the vicinity of this substrate. Okay. So, depending upon the way you transport those constituent elements, you call it vapor phase epitaxy. We will see one by one what it is. Liquid phase epitaxy, I gave you a glimpse of liquid phase epitaxy and I discussed about P type, N type dopant by adjusting temperature in the previous lecture. Molecular beam epitaxy. Okay. That if you talk to the materials people, depending upon what they have at their disposal, they will highlight on that thing. Okay. If you talk to MBE person, they will say that is the best. Actually, viewing objectively, each has its own merits, each has its own drawbacks also. So, you have to compromise depending upon what you want. So, let us see vapor phase epitaxy VPE of gallium arsenide. Here this involves the transport of species by some of the volatile compounds of the material. Okay. For example, if you talk of silicon, you would talk of vapor phase epitaxy, that is vapor phase epitaxy. You talk of the volatile compound, that is arsine, ASH3, or you talk of arsenic tetrachloride. Okay. I am sorry, silicon tetrachloride, I am sorry, not arsine, it is silane for silicon or silicon tetrachloride. Then release silicon from that. The reaction will be taking place on the surface of the substrate. So, that is the thing. In the case of gallium arsenide, you have to transport a compound containing gallium, you have to transport a compound containing arsenic, then force a reaction. In that reaction will occur if you provide the actual temperature etc. for the reaction to take place. Force the reaction at the substrate. You don't prefer the reaction to take place in the gas phase. Supposing I have substrate here like this, if the gas is flowing through that, you do not prefer the reaction to take place there. You prefer the reaction to take place on substrate, because in the gas phase, if the reaction is taking place, you have these gallium arsenide formed there, maybe it may be droplets of gallium arsenide coming out there. That is not what is required. You must have the reaction taking place just near the surface. on the surface, so that atoms can, once they are released, they move about and arrange themselves. That is called heterogeneous reaction. So, the reaction will be homogeneous if the reaction is taking place in the gas phase. The reaction will be heterogeneous if it is taking place on the surface itself. You are the favored, or the one that you like is heterogeneous reaction. To put it in simple terms, you want the reaction to take place on the surface. That is what happens when you heat the substrate, right there. Okay. Now, let us see. You can transport, see, after all, you have to transport arsenic and gallium. Today I am giving you the whole gist of epitaxy. If you start talking of this, you can talk for 10 hours on this. But just the idea, what is involved, what are the compounds involved, just so that you get a flavor of what is going on around. So, the transport of arsenic is done in the form of, in the vapor phase epitaxy, is done in the form of arsenic trichloride or arsine, ASH3. Arsenic trichloride is liquid, arsine is gas. Okay. Gallium is transported again in the form of a volatile compound, either as gallium chloride or trimethyl gallium. Okay. Now, depending upon the compound used for transport, you call it by different names. You call it that for vapor phase epitaxy. First, you have got 3 classifications. If you just go back, you have got 3 classifications depending upon the mode of transport. Here, it transport is through vapor phase compound. In the liquid phase, it is actually precipitation from the liquid phase. You keep the substrate in contact with the liquid. From the liquid, you precipitate those constituent elements. That is liquid phase. Whereas molecular beam epitaxy, physical transport of gallium, physical transport of arsenic in the form of a beam. That is why molecular beam. So, that particular point is that is why that one classification. Now, coming to the vapor phase epitaxy, depending upon what sort of compounds you use for transport of vapors, you call it halide process, hydride process, or MOCVD. MOCVD is one of the most popular epitaxial techniques for gallium arsenide today. Metal organic chemical vapor deposition or organometallic, both same. It is only who is talking. Somebody will say metal organic CVD or organometallic CVD. You deal with the same compound, trimethyl gallium. Okay. So, that is called depending upon that particular thing, you call it MOCVD. Okay. Now, let us just take a look at some of the each one of them in detail, not in detail, just going through the thing. Halide process, you can see here, this is a furnace tube, Potts tube, which is laid out there, and it is a 2-zone furnace. Fancy name given to that is a reactor. A reactor, epitaxial reactor is nothing but that. It frightens you when you say reactor, but if I say it is a furnace, oh, that is all. Okay. That is it actually. You have a furnace here or an epitaxial reactor which has got 2 zones. One zone where you can heat it about 800-850 degrees centigrade. Simultaneously, you must be able to heat other zone to 750 degrees centigrade for growth. So, the philosophy here is this, or the approach is, you have hydrogen gas and arsenic trichloride liquid. Okay. You have a bubbler, you pass hydrogen through that. Okay. Like this. I am just showing some bubbler, it may be glass. Then you have the arsenic trichloride, because a lot of chemistry comes here through with that with this lecture. Okay. So, this arsenic trichloride and a tube coming into that, you pass hydrogen through that. You pass hydrogen because you can get it in a very pure form. You don't want to use any gas which will add contaminants when you grow the epitaxial layer. So, pass hydrogen through that which is very pure, fixed on purity, and then you notice that is the liquid, and this bubbles hydrogen through that, and when it comes out it picks up the vapors of arsenic trichloride. So, what is transported now is the vapors of arsenic trichloride. That is what is shown here. Arsenic trichloride vapors entering there. What is before that I have not shown. That is the secret. Okay, it is what is present there. So, you control the temperature of the bubbler, you can control the vapor pressure. Once you control the vapor pressure, the extent of arsenic trichloride that comes in is controlled. So, the controller is there, that is the temperature of the bubbler. So, you can actually, so now rest is just chemistry, few equations we will see. Arsenic trichloride, notice here you have a crucible which contains gallium. Gallium is melt even at 30 degrees centigrade, it is the molten gallium. So, past this arsenic trichloride vapor comes here, this is for carrier gas hydrogen additional to dilution if you want to. So, arsenic trichloride plus hydrogen will react even at 425 degrees centigrade to give you arsenic in that form AS4 and HCl. Now, this arsenic which is coming out here will slowly react with gallium. Okay. Where you have kept the temperature at about 850 degrees centigrade, it will form gallium arsenide on the surface. You may have to keep for that reaction to take place, to form a crust of gallium arsenide on the gallium surface, you may have to keep it for several hours. When I say several hours, even 24 hours, so that a crust is formed. Now, so you have a top layer of gallium which is converted into gallium arsenide. Now, the gallium arsenide, now notice the first reaction that is taking place. You have arsenic which is reacting, you have also hydrochloric acid, HCl. So, this gallium arsenide with HCl will react, the crust which is formed, gallium arsenide, and this one here is again an arrow, left hand side is the reaction taking place, these are the reaction products. So, this reaction is either way it will take place. Okay. It will proceed from this to that if the temperature is high. So, you keep the temperature high 800 to 850, if you jack up the temperature to 850, this reaction between gallium arsenide and HCl will take place to release gallium chloride. See the whole effort, what is this whole effort about? Ultimately, you want to bring in gallium chloride here and arsenic here, okay, and force gallium chloride and arsenic to react to release gallium arsenide. So, this weapon that is used is this equation. This equation is a double-edged sword. It is a double-edged sword in the sense you can force the reaction to take place from left to right, that is from gallium arsenide HCl reaction taking place releasing gallium chloride and hydrogen and arsenic, that is taking place here because temperature is about 850 degrees centigrade. So, what is transported across into this is this thing, what is on the right hand side. Now, here you keep the temperature at 750 degrees centigrade, lower temperature, the reaction proceeds in the opposite direction. Same species which have been produced at high temperature recombine, this is the thermodynamics of the process that will release gallium arsenide on the surface. This is a graphite substrate, you keep it at an angle etc., so that to get uniform deposition all through. Okay. To get all through uniform deposition, you keep it in the tilted position. Okay. So that even if the vapors get depleted, okay, you get higher velocity, so that diffusion takes place more on this side. So, result is you get uniform layer from this end to that end. This is the graphite substrate which is heated, that is the semi insulating gallium arsenide. On the top of that you will realize this layer, that is this reaction taking place releasing gallium arsenide. So, that is the thing. Unit 2 zone furnace, with you can use gallium as the source to convert it to gallium chloride by the reaction of here, this reaction, HCl and gallium arsenide, and this, okay. And what you get when you bubble, so the whole process what I have discussed is summarized here so that it is available for you to see. The hydrogen is, of course, you can get 6-9 purity, that is, I use hydrogen as a carrier gas, all that I have mentioned. Now, the halide process is called hot wall reactor process, as I mentioned already. High quality gallium arsenide epitaxial layer of carrier concentration 10 to the power 13 per centimeter cube. You do not get semi-insulating there, because it is just a thing which where growth, where you are transporting some of these compounds which will carry some of the impurities. So, you get about 10 to the power 13 doping, undoped N type it turns out to be, because of some silicon contamination which comes from gallium source, okay, that has some silicon contamination, that is enough to give that doping concentration. And the arsenic trichloride, of course, you can get here. I just want to correct this, okay, because this particular quantity is 1,9 added there, and this also 1,9 added there, 7,9 purity, okay. Because of that purity you can get this such low doping level concentrations. If you do not have such purities, you will get 10 to the power 15, 10 to the power 15, okay. Now, that is the halide process, quite popular because you get layers which are quite pure. Next process is slightly different. The way you transport these, ultimately over here you get gallium chloride and arsine. So, instead of arsenic trichloride, okay, which you use in the hydrate process, halide process, use arsenic trichloride, which is used to release arsenic and also gallium. Gallium is released through gallium chloride. Arsenic trichloride converts gallium to gallium chloride. Okay. I hope the chemistry is right. Now, here same gallium is there, liquid form, all mechanism same thing, and arsine is let inside, deep inside. In the previous case, arsenic trichloride was coming right up to this point only, so that reaction is forced. Now, you straight away transport arsine there, and you have HCl also here, that is separately required. If you require, you can use it. Because before you start, I just didn't mention that in the previous thing, before you start growing the layer, you must etch the substrate in situ. Once the temperature everything is reached, or even higher temperature, you remove a layer of gallium arsenide. In the case of silicon epitaxy also, when you grow silicon, you just do not go and dump silicon on that. You remove a layer of silicon, so that a fresh surface is exposed using HCl etching. Here also HCl, hydrochloric acid etching, HCl etching is done. So, that is, initially you pass HCl directly to that point, which will actually react with gallium arsenide, and if the temperature is high, initially you keep it at 900 degrees centigrade. So, if you recall in the previous equation, HCl plus gallium arsenide will react and remove the H gallium arsenide if the temperature is high, but the products will be formed, gallium arsenide will be formed if the temperature is 750. So, you can see it here, just quickly go through that, because you can just see it in the looking into this. Arsine breaks up into AS4 and hydrogen. Then here HCl is passed also onto this. Previous reaction, you converted the gallium to gallium arsenide and you allowed arsenic trichloride to react with that, to release gallium chloride, to transport gallium. Here HCl is directly supplied to react with gallium to release gallium chloride, and gallium chloride with this gallium chloride and this arsenic will react to give gallium arsenide, deposit here at 750 degrees centigrade. Okay. This reaction would have been opposite direction if the temperature is high. So, that is actually the hydrate process. Whatever I have said is written here. Arsine is used for arsenic transport. Purity of arsine is lower than that of arsenic trichloride. Arsenic trichloride purity is about 7 nines today. About 10 years back it would have, or 10-15 years back it was 6-9, now 7-9. Whereas arsine purity is still about 5-9 purity. Okay. So, result is the layer that you get, you cannot go down to those doping concentrations which are 10 to the 13 undoped, but you want undoped 10 to the 15, no problem, you can use this arsine. Okay. So, the difference here is the ratio of arsenic and chlorine can be varied very easily, because they are different sources. If you are using arsenic trichloride, ratio of arsenic to chlorine is 3.33. So, you have bit more flexibility for deposition, that may not be a big advantage, but then that is one of the merits. Hydrate process of course is there is okay. If you just go back to the previous thing, you will see in the hydrate process or the halide process, first process, arsenic trichloride, you have to convert gallium to gallium arsenide. That takes long time, 24 hours I mentioned. Whereas if you use in hydrate process, there is no such conversion. Go back and see here. Straight away gallium chloride is released by reaction of HCl and gallium. In the previous process, go back further down, in the previous process you release gallium chloride required for gallium by reaction of arsenic trichloride, arsenic gallium arsenide formation here. So, that process is not there, that is what he mentioned here. That is, it does not take, you do not have to wait for that gallium arsenide crust formed on gallium. Straight away pass HCl, that will convert gallium to gallium chloride. Coming to the third process, that is MOCVD or metal organic chemical vapor deposition. I just want to give a word of caution. Vapor, we are talking of vapor phase epitaxy. Sometimes it is also referred to as chemical vapor deposition. It is a generic term, general term that is used. When you say chemical vapor deposition, it may be epitaxy or may not be epitaxy. See, what we are talking of is all these processes where chemical vapor deposition, because the transport is through the chemicals, vapors of the chemicals, arsenic trichloride, arsine, they are all the vapors. So, chemical vapor deposition. Okay. Now, same thing that we talked of, if you use silane with silicon at lower temperature, it is not single crystal, that is not epitaxy. But if you take a single crystal substrate, on that use proper temperature, then use the chemical CVD, that becomes vapor phase epitaxy. So, the correct term is vapor phase epitaxy. In fact, even here they should have used metal organic vapor phase epitaxy, MOVPE. People use it, but general term is MOCVD. So, this is epitaxy. So, what we are telling is, if you use MOCVD on a foreign substrate like molybdenum, you will get polycrystalline material. So, if you use MOCVD on a single crystal substrate like gallium arsenide, you will get single crystal. So, here it is a similar process, much simpler. All that you do is, here this is, since it is a pyrolytic decomposition, you can use a substrate, graphite substrate heated by RF, radio frequency coupled to the substrate alone. When you do that, the deposition will take place only on substrate. In a hot wall epitaxy, deposition will take place not only on the substrate, it will deposit on the tube also. So, you have to remove the tube every time, clean it. Okay. Here also some deposition will be there, but major deposition will be here. See here, the organometallic compound is used for transporting gallium, and for transporting arsenic, arsine is used. Okay. Not so high purity like arsenic trichloride, but you put up with that. So, CH3 thrice gallium is trimethyl gallium. Okay. So, that is bubble, hydrogen is bubbled through that, bubbler is shown here, which is maintained at some temperature, usually 0 degrees, easy to maintain, put ice and maintain, and then that is passed through the thing. And this trimethyl gallium, and in another tube you have got arsine coming up, and over here you maintain the substrate temperature at about 650 degrees centigrade, that is sufficient for epitaxy of gallium arsenide, 650 to 750. So, 650 degrees centigrade you maintain, and then you will have this reaction taking place on the surface. Okay. To release gallium arsenide and methane, you can see the simple chemistry also is simple here, one chemical reaction taking place there. Okay. So, but more than that, you actually have the merit of using this particular RF, plus you can use this for growing gallium arsenide, use another bubbler which has trimethyl gallium and trimethyl aluminum instead of CH3Ga, CH3Al. Okay. What will you get? I have one bubbler which takes trimethyl gallium vapors, one more bubbler I attach to take trimethyl aluminum, and arsine gas. What will you get? From trimethyl gallium you get gallium, trimethyl aluminum you get aluminum, arsine you get arsenic. So, you get aluminum gallium arsenide. Such a process is not possible with the other two processes which we have discussed, because the aluminum compound, if you have to realize, you have to go to 1100 degrees centigrade. Whereas here the aluminum compound is organometallic compound or metal organic compound, aluminum trimethyl aluminum. This is one of the key merits of MOCVD. Trimethyl gallium, trimethyl aluminum, you can tell names, trimethyl indium if you want indium, trimethyl zinc if you want zinc, dope it with p type, put another bubbler. So, either you can call trimethyl zinc TMZ or diethyl zinc DEZ, without anything names you want. Those are some of the things. So, the merit of this metal organic CVD is you can get binary compounds like gallium arsenide, you can get ternary compounds like aluminum gallium arsenide, gallium indium arsenide. You can also dope them with zinc, with using diethyl zinc or trimethyl zinc. Okay. And of course, you can add dopants like sulfur, use another bubbler, that means you will have all bubblers hanging around, okay, connected to the system reactor. Sulfur, okay. You can use hydrogen sulfide or you can use sulfur monochloride. That is sulfur. After all, what you need is a compound of sulfur, hydrogen sulfide or sulfur monochloride. You can add those things, bubbles. The sulfur monochloride is liquid. Okay. In fact, one of the systems which we have been working at Rensselaer way back was sulfur monochloride, this system. Okay. That was used for growing gallium arsenide of molybdenum, thin layer of molybdenum, gallium arsenide doped with sulfur to make solar cells. There is a huge program on gallium arsenide based solar cells, and grow it on molybdenum substrate, it turns into polycrystalline. Okay. Now, this is MOCVD in very nutshell, that is the thing, all the advantages I have just told you already. These are put down here. The growth rate is about 0.1 to 0.5 micron per minute. If you want 10 microns layer, at least about half an hour or something like that you may have to put. 0.3 micron means we used to grow about half an hour to grow 10 micron layer. That is why that, remember that number. So, this growth rate you can control by controlling the partial pressure of trimethyl gallium. You have plenty of arsenic in all these cases, you must have plenty of arsenic. Why? Arsenic overpressure must be maintained, otherwise you lose arsenic from the growing gallium arsenide. So, all through you put excess arsenic there to maintain overpressure. That is done here also, that arsenic is maintained at overpressure, but growth rate is controlled. How much TMG is there for reaction to take place? Excess arsenic is there through arsine. Now, more TMG you add, more will be growth rate. You do not want to have excessive growth rate. The crystal will be better if the growth rate is smaller, because it has enough time to organize itself. So, you prefer smaller growth rates. Okay. Advantage of MOCVD is ability to grow aluminum gallium arsenide, indium gallium arsenide, etc., which I have said just now. You can use trimethyl aluminum for transporting aluminum. This is not possible with halide. This is just a system which is shown schematic MOCVD system, which what all I have mentioned just now. You can have trimethyl aluminum bubbler, trimethyl gallium bubbler, diethyl zinc bubbler to dope p type if you want to, okay, and all of them you can bubble hydrogen through that. These are all the valves which will be opened and closed by means of hydraulic, that is air pressure. Okay. You press a button, that valve will open or close to letting that. If you do not want to dope it, you close this valve. If you want to dope it, open that, both of them. And then of course you have got arsine bubble through that, straight away coming in, and hydrogen sulfide coming in here. So, those are for doping if you require. Trimethyl gallium gives you the gallium arsenide. Okay. So, the last one that we have here is the molecular beam epitaxy. The molecular beam epitaxy is different from the vapor phase epitaxy in the sense that constituent elements are directly transported in the physically. A very good example of physical transport, I am sure all of you are familiar, is vacuum deposition. What do you have in a vacuum deposition system? You have chamber in which vacuum is created, you have a filament which can be heated, and you keep, for example, if you want to evaporate aluminum, that is you want to transport aluminum onto silicon or gallium arsenide, what you do? That filament is heated, you put aluminum there, heat it, it melts and evaporates, and it goes all over and onto substrate. Okay. Now, same thing is done here, physical transport. This is nothing but a physical transport. Now, you call it molecular beam because it is not because just molecules. You will have different effusion cells. These are the different cells, crucibles, which are heated. Okay. Just like putting a coil and putting some evaporant, you have these crucibles which you call it as effusion cells. Sometimes they call it as K cells, Kuntzen cells. Okay. These are some of the jargons which the MBA people throw at you. It is just a source which is heated, crucible which is heated. There is a heating coil that is put around that. Now, there is shutters all around here. Okay. So, the entire thing is a stainless steel chamber which is evacuated by means of complicated pumping systems, oil free pumping system, okay. And each one is the cell which is used for, let me use that language, evaporation. It's okay. People may not like if I say evaporation, it is actually physical transport, let us say, of gallium, pure gallium, 7-9 purity gallium is put inside the cell, you have to fill that in. Arsenic, real arsenic is put, poisonous, deadly poison. There is always a joke which tells what is poisonous to us is good for semiconductors. You look at the gases, look at the substance that you are using. So, it is only as a lighter sense, do not take it literally. Okay. So, it turns out so. So, arsenic, and if you want aluminum, put aluminum here, indium, you put indium here, whatever you want to put there, the sources. Okay. So, what you do is whatever, and dopant if you want to put, you can put it there. Okay. So, you can get the required layer of the material, gallium arsenide, indium gallium arsenide, etc., by using the proper source. Now, the substrate, the single crystal substrate is put here, and it is attached onto a heated substrate, and the substrate is molybdenum. Molybdenum is used because it is a good thermal conductor, that is chosen because of that. And how is this mounted on that? It is mounted on that using indium for mounting, and of course, indium melts at 150 degree centigrade. Even gallium can be used, but it is held there due to surface tension. even it melts there, this is held onto the substrate by means of surface tension. So, now the key thing here is this actually goes as a beam, and if it will go as a beam if it is not colliding. It will collide with any of the particles if there are particles. What are those particles? If it is atmospheric pressure there, what will happen? When you evaporate it, it will not go there. It will just collide and it just collapse near that. In fact, if you take a vacuum evaporation system and if the vacuum is not proper, aluminum will not go to the substrate, it will just there spread out. This is one thing which you have seen. So, you have to create a vacuum of at least 10 to the power minus 5, so that the mean free path length is much larger than this gap. This will be about 30 centimeters. The distance between the source and the substrate will be about 30 centimeters. So, you must be much larger than that. A calculation shows if I have about 10 to the power of minus 5 torr, 1 atmosphere is 760 torr. This is 10 to the power of minus 5 torr. If you use, the mean free path is at least 10 meters. So, you can be happy with 10 to the power of minus 5 torr, but if you grow gallium arsenide at that pressure 10 to the power of minus torr, and this substrate heated to about 600 degrees centigrade. Why do you heat the substrate? The atom should be able to move. If you heat that, okay, if the vacuum here is 10 to the power of minus 5 torr, you will get gallium arsenide, but that will be, to use a harsh word, that will be junk. Junk in the sense it will have lot of impurities which are coming up from this ambience. So, if you want to reduce the contamination level by another 10 to the power of minus 5 factor, you have to go down in vacuum by another factor of 10 to the power of minus 5. So, the vacuum level that you are talking of here is something like 10 to the power of minus 10 to 10 to the power of minus 11 torr. Very high vacuum, ultra high vacuum, that is UHV is ultra high vacuum. And okay, so the constituents of this MBE system are these K cells which are the sources of evaporant with shutters which can be opened or closed whichever you want. All of them are heated. You close it, all the things you close. If you want only gallium arsenide, open only these two shutters. Okay, that is the idea. And these shutters can be computer controlled. So, what we are telling is very high vacuum is created, and that is done by using special pumps. I will not read out that. There are all sorts of pumps which are available which are oil free. Now, what you have here is most important thing that I want to point out is I just drawn a circle there or ellipse there. This chamber is made up of stainless steel, high quality stainless steel if you want to get down to those vacuum. And before deposition, you heat the chamber to high temperature to degas and pump down. All that is done. Not only the chamber is stainless steel, you know, when you have this looks totally closed. There are ports somewhere in these things. There are ports which stainless steel projecting out with, you know, with gaskets and valves, doors which can be closed. That is not shown here. So, to get inside, to put all these things, wafers, loading, etc., you need those things. So, when you close a chamber like that, there will be a gasket. You can't use any gasket that you like. So, what you use will be metal gaskets. Metal gasket, what metal? Hold your breath, gold. Okay, gold gaskets are used between those two. So, those are some of the things that one does to get high vacuum, and the entire process of course is simple. Control the flow of gallium and arsenic by adjusting the temperature, the beams which are coming. You get the beams because of the very high vacuum, that is why you call molecular beam. So, it is coming like that from beam, another one like that onto the substrate. So, you can get gallium arsenide, very high purity gallium arsenide, 10 to 13, 14, etc. Now, that is the pumping system, and you can get, the advantage here is you can grow 1 micron per hour, very small growth rate you can do. When you grow very small rate of growth, very high purity, excellent crystal quality you get, okay, and thickness uniformity over a 5 centimeter wafer you can get within 1%. So, people who want to make quantum wells, very small layers, they resort to this. Today, MOCVD is competing with this to grow thin layers. Okay, let me just warn you and leave on that. That is, MBE is very good, MOCVD is competing, because mass production if you want, MOCVD is better than this. So, high purity material can be grown, and any composition you can get, indium gallium arsenide, and also any dopants that you can use. Key thing is control of thickness, control of impurities precisely done to the extent of a monolayer. Okay? And some of the other advantages are that you can just say, you can actually introduce some of the diagnostic tools along with this thing. Okay? Now, let me not go into these details onto that right now. Okay? Let me just sum up at this stage. The MBE system has gained a lot of popularity, and it has today people are accepting to use this for some commercial applications because of the high quality that you get. Particularly those who want very thin layers, for example, aluminum gallium arsenide, then gallium arsenide, a very thin layer, okay, at the angstrom level, then you use this type of approach is highly attractive. So, this is one of the most popular techniques which is used along with MOCVD. Other two techniques, hydride halide, it's more of academics, but still a poor man's quality will be that layers will be some of those high quality. If you want, you use that halide process. So, with that, I think I will stop discussion today. Few of the things which are meritorious for gallium arsenide growth with MBE, I will bring out tomorrow. Then we will go on to the devices afterwards. We will see you in the next lecture.